Thank you for the opportunity to making a presentation here. Today I give the topic on the Thermo-Mechanical Metamaterials. It's towards the stimuli-responsive micro-robots. So here it's my working mechanism of the project. We use the bimaterial beam, as you can see here. It's made up of two different materials, and this bilayer beam will expand and bend upon heating due to the difference in thermal expansion, like this. Also, if you cool it, it will deform in the opposite way. Here in the project, we will use this thermo-mechanical process as the deformation initiator. Like we use this thermal actuation for the soft micro-robot. So here I show on the left image a real robot arm. For a robot arm, you should finish the pick and place task. So on the right image, here is the controlling principle of our project. As you see, we built a 3-axis setup to complete the three-dimensional movements to finish the pick and place task in each axis. And you see, we have two kinds of blocks. One is for the rotation and one is for the translation. By combining the 3 axes and the translating and rotating in each axis, you can just finish all the pick and place tasks. Here, let's first focus on the translation blocks first. As you can see, this is a translation unit cell. Still, it's made up of two different materials. They are depicted in red and blue. As you can see, for this unit cell, if you hit it, each beam like this, each beam will expand and bend, thus creating the overall upwards translation like this one. So using this unit cell, here we use 5 unit cells to build a lattice. As you can see here, for this lattice, it's again, if you hit it, you will get an upwards translation. That is just one of our robot arm. And realizing this, we should stress that the performance of the lattice or the cell can be changed as you can change the parameters. Here we demonstrate the relationship between the translation moment and the design variables. Here the two main built-in parameters are the length of the bilayer beam and the difference in thermal expansion. As you can see that they are both presenting a linear relationship with the movement. So following this rule, you can just change the performance as you desired. Also, we want to investigate the actuation force the unit cell or the lattice can offer to move an object. We place a load here on the extended lattice. Again, if you hit it, it can move the object by a certain displacement. Here we refer the model of spring and mass. We note that all the loads are normalized to the mass of the structure itself. Certainly, as you can see, for large loads, you can move it by fewer displacements. But you can see that within the linear stage, you get the inverse linear relationship between the displacements and the mass you can move. It should be noted that we use 5-layer unit cells, so you can just increase the amplitude of the moving displacements by just increasing the number of layers you use. Now let's see. This is for the rotation function. Again, we use the bimaterial beam. As you can see, if you hit it like this, all the bimaterial beam will expand and bend, thus creating the overall moments. I mean, here is the rotation of the upper end. Here is the direction of the rotation angle. So if you use the unit cells to build several layers, that is a lattice here, you can see the lattice here. for this set of parameters, you find that we can get a rotation angle as large as 16 degrees. That is fairly enough in practice. And again, we note that you can increase the rotation angle of the top end by just increasing the more layers. Also, this is a relationship between the movement and the several main parameters in designing, and it's similar to the translation, so we don't give any details here. Also, for the robot arm, it should be able to rotate an object by a certain angle. So here we investigate the actuation capacity of this rotation style by referring the polymath model like this. Here, it's similar the relationship as the translation structures. And one thing we should note is that for this parameter, this design unit style, it can move a normalized mass up to 10 power 10. This is fairly enough in the robots and something else. Finally, I want to present some details on the fabrication and experiments. As I have mentioned before, we use two materials to build these functional structures, but in the lithography, it's by no means easy to fabricate a complex structure by using two different materials. So here, our strategy is that the two materials are written by using the same polymer. I mean, absolutely the same polymer, but with different litho pore. So the two materials, they will resemble each other, but rather different in thermal expansion. So the difference of thermal expansion is just the key to our project. And I show the here. So here it's for the initial litho pore for the two polymer are 45 milliwatts. So here you use different power, and you see the structure here, and yeah, it's like this. You see some pre-bending, and I will talk about this pre-bending later. Here I show the optical image of a unit cell and the lattice. You know, for the optical image, it's not very clear for the bottom structures. And you see the shadow here. In fact, these shadows are the unit cells downstairs. So, and you can observe very obvious pre-bending here. The pre-bending is inevitable, but within the linear stage, this pre-bending is not. It has no influence on the final results. Instead, as you see the same image down, you can see that the pre-bending can also serve as an evidence that the whole structure will deform in our design manner. As you see, it's the pre-bending leading to the rotation, as you see here. So here, we show the video. This is the optical experiment. Maybe it's not very obvious because the angle is not large enough. And let's trace it again. See, it's rotating and going back to its original position. And downstairs is see, it's rotating in the anti-clockwise direction. Sorry. Maybe you should keep your eyes on this because it's not very clear again. So here, so on the right image, I show the experimental and simulation results. This black line, it records the heating process, while the red one, it records the cooling process. And you can see that we increase the temperature uniformly, so you get almost a linear relation between the rotation angle and the temperature increment. This trend is well in agreement with the theoretical prediction, and you find that the black one and the red one, they almost coincide. That means that this large deformation is well reversible. So this is important in the practical applications. But you see, we did witness some errors between the simulation results and the experimental results. Part of the errors mainly come from following aspects. One is the measurement of the thermal expansion of these two polymers, and also we have some errors in recording the temperatures we hit. Finally, it's inevitable that we have some manufacturing imperfections for all the structures. So these main factors contribute to the difference between the theoretical one and the experimental one. And sorry. So here it's about the translation blocks, and you can see in this image, you can see that again the bimaterial beams has the pre-bending, and also this pre-bending has led to the overall upwards translation, and you see it's moving upwards now. And down the images we have shown the extended lattice. This lattice we use 4 blocks just to make it more stable. And I'm very sorry that we haven't still got very perfect results for experimental results for the translation. And it was delayed long ago due to the coronavirus. And we shall continue on this once our lab is open. So that's this, and thank you for your attention. This is my group supervisor and the main researchers.